Hi, I'm Sarita Adve. Welcome to the presentation on ILLIXR, an open source testbed to enable end-to-end extended reality systems research. I lead this project with my senior graduate student, Muhammad Huzefa, and a large team I will acknowledge on my slides. Extended reality, or XR, including virtual augmented and mixed reality, will be the next major computing interface and has the potential to transform most human activities, including science, medicine, education, and more. However, there are many challenges to overcome before we can achieve the full potential of XR. There is an orders of magnitude gap in power, performance, and quality of experience between the systems we have today and the systems we desire. For example, for full immersion, we would like about 200 megapixels resolution, but current state of the art delivers about 7. To wear AR glasses all day everywhere, compute power needs to be in the hundreds of milliwatt range versus the 7-watt state of the art we have today. There are similar large gaps in other metrics, and I refer you to our paper for those. As we see the end of Moore's law, achieving such improvements would be challenging for any domain. XR comes with additional challenges. First, designing an XR system requires diverse expertise, including in graphics, vision, audio, video, optics, and haptics. Second, metrics to measure the goodness of an XR system are complex and still a subject of research. XR requires multiple user-driven, end-to-end quality of experience metrics such as motion to photon latency, image quality, audio quality, and more. Third, to get the performance benefits we need, we cannot rely on just one layer of the system stack. We will need cross-layer system optimizations where we co-design the hardware, compiler, OS, and the wide range of algorithms for a complete XR system. Additionally, it is unlikely we will be able to meet all XR application demands within the end user device. So we will need co-design across the end user device, the edge, and the cloud, which will serve as a back-end infrastructure for serving single and multi-user XR. Finally, when we started our work a few years ago, the biggest challenge actually was that XR was dominated by a few participants with closed proprietary systems. There were no open reference systems or benchmarks to jumpstart XR systems research. In other words, there was a large barrier to entry for open R&D in XR systems. We asked the question, how can we democratize XR systems research development and benchmarking so a broader community can participate to address the challenges to move this field forward? So this is how ILLIXR started. ILLIXR stands for the Illinois Extended Reality Testbed. This is the first fully open source end-to-end XR system. ILLIXR has state-of-the-art XR components connected with a modular and extensible runtime. It is compatible with OpenXR, a recent standard that provides an open interface between XR applications and the system. We have performed an extensive characterization of ILLIXR to identify the performance, power, and quality bottlenecks in XR systems, and we are using ILLIXR in a large number of research projects. To show that ILLIXR is a real working system, I would like to next show some demos. This demo shows how we use ILLIXR for day-to-day work, debugging on a regular monitor without a headset. In the grayscale window at the bottom, my student is walking around in our lab and we see the view of his physical space from his camera. The window on the upper left shows a third-party view of the virtual space that my student is navigating. You can see the position of the headset in the virtual room as determined by ILLIXR. This third-party view helps us debug our system. At the top right are the eye buffers that ILLIXR outputs for the user to see on the display. At the bottom left is a debug view window to provide a range of information to help understand and debug the system. Hopefully on your screens you can see that ILLIXR is able to give a smooth experience with good tracking. In the next demo, we have Joseph with the North Star headset, which we use only as a display. The pixels being displayed are generated by ILLIXR which is running on this very novel mobile PC infrastructure that Jeffrey is rolling around. We can see what Joseph is seeing on the headset on the right side. He's running the famous Sponza application navigating a castle. You can see that ILLIXR is tracking smoothly and rendering works well too. Note that this is a completely open source end-to-end XR system that you can modify however you like and measure whatever you like for your research and development. Now, if Joseph wants to walk around without his friend, he can run ILLIXR on the backpack PC you see here. Again, he's enjoying the nice Sponza experience running ILLIXR on the backpack. Although ILLIXR is giving him a nice experience though, so far it has been running on a beefy PC with a high-end GPU taking a lot of power. On a weaker embedded class system like the Jetson, for example, the experience is not so good. So it's clear that we have a long way to go before we can put everything desirable on the headset form factor with the power envelope we would like. So our next demo is about recent work on ILLIXR to offload some computations from the headset to a remote server. On the right side, you can see the backpack PC at the bottom representing the end user device running ILLIXR and the iBuffers it displays on the monitor at the top right. On the left is the server for offload at the bottom and its monitor at the top. In the center is the third-party debug view again. In this configuration, ILLIXR is offloading head tracking to the remote server over the network, and you can see again that tracking is able to tolerate this latency and works well remotely while saving power on the end user device. ILLIXR already provides an open testbed with rich features for the community, but there is a lot more to be done, and we realize that we cannot do this alone. So for this reason, we have launched a consortium with several industry and academic partners, including ARM, Meta, Micron, Northstar, NVIDIA, and so on. We have three goals with this consortium. First, we would like to evolve ILLIXR into a reference open source testbed based on consensus from the community that can then be used for a wide range of research, development, and benchmarking. So to do this, we would like to generate consensus on the components and the interfaces to those components, support a modular and extensible runtime, and provide extensive telemetry. We believe ILLIXR already provides a solid foundation for this, but a lot more work is to be done. We would also like to create a standardized benchmarking methodology with accepted and curated applications and data sets, consensus system configurations, and metrics for how to measure the goodness of these systems. Finally, we would like to build an XR systems research and development community that can work together to move this field forward. So these are the three goals of our consortium. So next, let's take a deeper dive into ILLIXR. But before I go ahead, I want to acknowledge the large team of students, collaborators, and consultations that has made ILLIXR possible. In particular, I want to call out my senior grad student, Josefa, who will be graduating soon, and he has led this project with me from the start. So next, let's do a deeper dive into ILLIXR. ILLIXR consists of three interacting pipelines commonly present in a generic XR system. The perception pipeline, which determines where the user is and what the world around them looks like. The visual pipeline generates the pixels that are displayed to the user based on their perspective or pose that's determined by the perception pipeline. And the audio pipeline, which plays spatial audio, also based on the user's pose. The various components in these three pipelines interact with each other through the ILLIXR communication interface and runtime. Now, ILLIXR is able to run XR applications written to the OpenXR interface. We do this by leveraging Monado, an open source implementation of the OpenXR interface. Today, all of the ILLIXR components are in software designed to run on a mobile device. In the future, we also plan to include support for hardware acceleration of these components. Also, as I showed you in the previous demo, we are now able to offload some components of ILLIXR to remote servers, but this work continues. So now let us look at each part of ILLIXR in more detail. I will be focusing primarily on a single device view. So most of what I'll be showing you the rest of today will be ILLIXR running entirely on the end user device without offloading. So the first one is the perception pipeline, which includes interfaces to sensors such as cameras and an IMU or inertial measurement unit to provide the input to the rest of the system. The next component is visual inertial odometry, or VIO, which provides the position and head orientation or pose of the user. VIO works at camera frame rate, which is relatively slow. The IMU integrator interfaces with the IMU and the VIO to provide higher frequency pose estimates. Next, the last part of determining the pose is the pose predictor, which extrapolates the pose from the IMU integrator to future timestamps, which will be needed by the visual and audio pipelines, as we will see. ILLIXR also has a scene reconstruction component, which uses RGB depth camera to build a dense 3D map of the world. Finally, we provide eye tracking to determine where the user is looking, and that can be used for various other downstream components. Eye tracking today is running from an offline data set, so it's not fully integrated in live experiments, but this work is ongoing. In the visual pipeline, the first component is asynchronous reprojection, which is critical to address the motion to photon latency, which is a critical a metric for XR. So the application takes the user's pose to render a frame from the user's perspective. However, this pose may change between the rendering start and finish. Reprojection obtains a fresh pose to update the rendered frame quickly to the new perspective. It also uses pose prediction that I mentioned in the previous slide to predict the pose for when the frame will actually be displayed, and reprojects the frame based on this final predicted pose. The visual pipeline also corrects for distortion due to the optics of curved lenses. And finally, it supports computational holography to deal with the divergence accommodation conflict and resulting fatigue caused by current displays with a single focal plane. This component enables displays with multiple focal planes and computes a per pixel phase shift for such a display. Now, we do not have such displays in our lab, so what ILLIXR is doing essentially is just doing the computation, and then the pixels are not displayed if we have this component on. Okay, the audio pipeline consists of a spatial encoder which encodes multiple sound sources into single higher order ambisonics virtual sound field, which can be easily manipulated for playback based on the user's pose. The playback component then obtains the user's current pose and accordingly rotates and zooms the provided sound field. It also provides binauralization to account for the user's ear, head, and nose. So I've talked to you about many ILLIXR components, but ILLIXR is not just a set of components. It is a complete system with a runtime that orchestrates the system's data flow. So let us see the XR system data flow. We start with the IMU that runs at a high frequency, and then we have the camera running at a lower frequency than the IMU. Both of these feed into VIO, or the odometry component. VIO and IMU feed into the IMU integrator, which runs at a high frequency again. We also have eye tracking going on. We have scene reconstruction, which takes the camera output. Reconstruction, IMU integration, and eye tracking feed to the application. The application sends its frame, the IMU integrator sends its pose to reprojection, and then this goes to the hologram. At the same time, we have audio encoding and decoding and playback happening. So this is a fairly complex system with different components working at different frequencies, with multiple interacting pipelines, with synchronous and asynchronous dependencies. So the solid lines here show hard dependencies, the dotted lines show soft dependencies, or what we call asynchronous dependencies, and multiple quality of experience metrics. And ILLIXR supports all of this through the ILLIXR runtime. So we've designed the ILLIXR runtime to be modular and flexible to enable a variety of research and development. ILLIXR components are plugins that are separately compiled and dynamically loaded, and we can easily add new components and swap new implementations for a given component. It's fairly flexible and easy to configure and use. The runtime also provides an efficient and flexible communication interface. So each component specifies the event streams. It's based on ILLIXR is based on an event stream interface where each component publishes or subscribes to the components that it wants to work with synchronous or asynchronous consumers. The runtime uses shared memory, providing a copy-free, efficient implementation. So overall, we have an end-to-end system that balances both flexibility and efficiency. For applications, we can write XR applications directly to ILLIXR, or we can also ILLIXR also supports OpenXR applications using the Monado Group's implementation of the OpenXR interface. And the experiments you will see today are run on the Godot game engine, which is an open source game engine supporting many applications. Today, ILLIXR runs on Linux, and our support for popular engines such as Unity and Unreal is following their OpenXR Linux support trajectory. ILLIXR provides several end-to-end quality metrics, such as motion to photon latency, which measures the time from head motion to display, state-of-the-art image quality metrics such as SSIM and flip, and also more conventional metrics such as frame rates, missed frames, time distributions, power, etc. Finally, here's a summary of all the components that ILLIXR supports today. For several of these, we support multiple algorithms and implementations. We can configure and study ILLIXR with an appropriate subset of these using live or offline datasets. Next, let us discuss the findings with ILLIXR. The first thing we found was to tune a specific configuration was a lot of work. There are many parameters and hand tuning takes a lot of effort. This already motivates a research agenda for automatically tuning XR systems and is part of our ongoing work. We ran ILLIXR in the configuration shown here on a high-end desktop machine as an upper bound for performance available today, and on embedded class machines more representative of what we'd see in a headset. We ran applications with varying graphics intensities. So we have a lot of characterization, lots of evaluations, and many results that I cannot go through in detail today. But just to give you a flavor of what we can do with ILLIXR, we can measure frame rates. So we did that across the desktop and the Jetson high power, low power modes for the different applications. We measured execution times and distribution for the different components of ILLIXR. We measured, where each component of ILLIXR was spending time in, or rather, which component was ILLIXR spending its time in. We measured the power, which component was taking more power versus less, which parts of the system, right, the SoC or the memory or the GPU, which parts of the system was spending, how much power. We measured various quality of experience metrics such as motion to photon latency, image quality, and so on. So these are the first published performance power and quality of experience results for an end-to-end XR system. I will refer you to our paper for these results. What I'm going to do next is give you a very quick overview about the implications for system designers that arose from these results. And certainly for us, for my group, this has set almost I would think a 10-year research agenda for my group, understanding these implications and what we need to do for system design. So the first obvious result was that indeed, we confirmed that there's a substantial performance power and QoE gap. And so we need to specialize the hardware, software, and the entire system and exploit heterogeneity and specialization to bridge this gap. Second, an interesting point was that there is no application component, no XR system component that dominated all of the metrics of power, performance, and QoE. So we need to consider all the components in the system together, which makes for a challenging system design. Power consumption goes beyond the CPU, GPU, and DDR memory. We need to consider system-level hardware components such as display and I/O. This is something that's traditionally not given much attention to in the architecture community. And there's significant variability in the performance profile. So we need to be careful about partitioning, allocating, and scheduling system resources. Finally, per component metrics do not capture the quality of experience. So again, we need to look at the entire system to make QoE-driven trade-offs. And then we also evaluated each component standalone and found a large diversity in the tasks, the compute and memory primitives. There was need for flexibility, need for programmability, and need for approximate computing. And again, I will refer you to the paper. My goal here is to point out that ILLIXR, it provides for a really rich playground for systems research, and there is a lot of research to be done. So stepping back just for from a sort of a high level view of what these results show. These results show that we really need a new style of research in the systems communities. In particular, they reinforce that meeting the requirements for XR does require a new style of research where we co-design across the stack from semiconductor technologies to hardware architecture to programming languages and compilers, systems runtimes, and algorithms and applications. And it's not just that we are looking at one end user device, but the true promise of XR is not going to be in this one device in isolation, but rather a number of interacting devices with different capabilities, providing multi-user experiences. And furthermore, the true promise is going to be seen where these devices are in globally distributed ecosystem with edge devices, edge servers, smart routers, and cloud services all coming together and bringing to bear their potential and their attributes to solving this problem and providing the end user with the experience they need. And all of this needs to be co-designed. Finally, driving this entire ecosystem will be the user experience. A bad user experience can physically affect the user in this case, causing disorientation, fatigue, headaches, and even nausea. Thus, XR requires end-to-end QoE-driven co-designed systems research, and ILLIXR enables all of this. So ILLIXR is being used today in a large number of research projects. Let me take you through a whirlwind tour of these just to give you an idea of the range of activities. With Gage Hills and David Brooks at Harvard, we are using ILLIXR for 3D integrated sense, compute, memory, and communication for XR, reflecting co-design of semiconductor technology and hardware architecture. With Vikram Adve and Sasha Misailovich at Illinois, we are looking at how to represent heterogeneous parallelism in software. We are using our previously designed HPVM compiler IR to provide a compilation and programming stack for heterogeneous workloads such as ILLIXR. With Vikram Adve, David Brooks, Vijay Reddy, and Guyan Wei, we have been looking at automated generation and selection of accelerator hardware and software. We've also been looking at accelerator communication interfaces and coherence and consistency issues, bringing in sensors and network interfaces as first-class members of a shared memory XR system. Another project is on automated approximation selection based on the ApproxTuner work with Vikram Adve and Sasha Misailovich. We're looking at end-to-end cross-component co-design in an XR workflow where we have seen large performance and energy savings for scene reconstruction as an example. I alluded to QoE-driven scheduling and auto-tuning of configuration parameters earlier, and we have a research project at Illinois for these goals. We also have a lot of recent activity on offloading to remote servers in collaboration with Ada Gavrilovska from Georgia Tech, others at Illinois, and with Intel. We're working with Ada and with Clara Narsted and Anthony Rowe from CMU for multi-user XR systems. Specifically, we're excited about integrating Anthony Rowe's Arena system, which provides services for distributed XR with ILLIXR so that we can get an end-to-end open multi-user distributed XR system. And there's a lot more going on, including work beginning on security and privacy for XR, on displays, on sensor computing, QoE metrics, and so on. We also have a lot of work ongoing on the testbed itself and the consortium. We are adding new components all the time, broadening the hardware and software platforms supported, creating data sets, etc. So I hope I've conveyed to you that ILLIXR provides a rich playground for XR systems research, development, and benchmarking. And I hope you will join our consortium to democratize XR systems research, development, and benchmarking. You can join our mailing list, our Discord, and our open meetings. Thank you.